Okay, so the general question I want to discuss is about a trade-off between power and efficiency. So we know that Carnot efficiency is an upper bound. This is good to know about this bound, but for practical purposes it is not really, if you want, relevant, because in that limit, assuming that you are able to get Carnot efficiency, in that limit the extracted power vanishes. So the practical question you can ask is, what is the maximum allowed efficiency if you want a given power output? And so I will mainly focus, I will little bit discuss also cyclic engines, but I will mainly focus on steady state heat-to-work conversion, so thermoelectric quantum systems. And in that case, there is a bound which was derived for scattering theory by Whitney a few years ago. This bound is purely quantum, is rather restrictive. And so the question, if it is possible to overcome this bound, if you consider interacting system, that's what I will discuss at the end. So the general question can be framed in the field of finite time thermodynamics. So as I said, if you have a Carnot engine, ideal Carnot engine, processes are quasi-static, and so the extracted power reduces to zero. So the question is, how much the efficiency deteriorates when processes take time in a finite time. So there is a field, finite time thermodynamics. You can investigate both steady state conversion processes or also thermodynamic cycles. And in every instance, it is clear that the efficiency at maximum output power is an important concept, because engineers try to, if you think about thermal plants, you want that they operate at the maximum output power. And of course, you would like that the efficiency does not deteriorate too much. Well, this is just a review paper if you are interested in this field. So if you can start by considering Carnot efficiency with two reservoirs. And okay, this is, if you look at Carnot engine, this is a reversible machine. So there is no dissipation. I say no dissipation, I mean that if you consider the one cycle, the total entropy production in that cycle is equal to zero. So it's reversible. Then the question is, we want now processes that take place in finite time. And there is this model by Curzon and Dalbord. And they have an internal Carnot engine which operates between internal hot and cold temperatures. And you conduct during your cycle the engine to reservoirs at external heat and hot and cold temperatures. And you have heat exchanges which take place. They are proportional to conductances for hot and cold exchanges with hot and cold reservoir, temperature difference, and the time you spend in contact with the reservoirs. So you have, well, you have internally, you assume that it is an ideal Carnot engine. So you have this relation between internal temperatures and heat exchange. And so if it is, you put all dissipation in the contacts. Internally, you have no dissipation. This is the approximation you make here. And then you can compute power output. And you get this expression. And now you want to optimize. What does it mean? OK, you can look at these differences between bath and internal temperatures. And it's clear that if these differences goes to zero, then heat exchanges are infinitely slow, and you get zero power. On the other hand, if internal temperature become coincident, then internal you have cycles with infinitesimal temperature, and so again, zero power. So in between, you can optimize power with respect to this temperature difference between internal and external temperatures. You get some expression for optimal internal temperatures. You get expression for maximal power. But what is interesting is that when you look at the efficiency at maximum power, you get a result which is independent of heat conductances, because it depends only on square root of ratio between hot and cold temperatures. This is result in this paper by Curzon and Albon, so it's usually called Curzon-Albon efficiency. Then it turns out that in the 50s, in the literature, engineering literature, it was already known, this result. And they point out that if you take a linear response, a small kernel efficiency, you get this eta C over 2. So since it is independent on conductances, there was, of course, it was discussed if this bound is universal. And it turns out that this is not the case, because you can consider another model, which is the opposite. Is called, the other was called endo-reversible cyclic engine. This is exo-reversible. It means that irreversibility is not due to contacts, but arises due to internal dissipative processes. So this is a model by Schmittl and Seifer. You have a cycle, a kernel cycle, and is investigated in the framework of stochastic thermodynamics. Is review, if someone is interested. So your particles are exposed to a time-depending trapping potential, and you can look at how the probability densities for your particles evolve in time. And if the model is interesting because it's solvable, it's exactly solvable. If you work, you can work out a Fokker-Planck equation. If you assume that a distribution is Gaussian at the initial time, it remains Gaussian. And then you can compute, again, perform optimization, compute efficiency at maximum power, and you get a different expression, which is known as Schmittl-Seifer efficiency at maximum power. And you have this expression where you see there is this factor gamma, which is related, it depends how the ratio of the entropy that you produce during isothermal hot and cold steps of your cycle. For the symmetric case, you get 1/2. And again, if you expand within linear response, you get eta C over 2. And I will just show another model. So it's not universal, but I will show another model. This is due to Van den Broek, Esposito, collaborators. It's a kind of low dissipation engine. So the argument is that entropy production vanishes if you are in the limit of infinite cycles for a kernel cycle. And so if the time of your cycles, TA, for cold isothermal and hot isothermal, is infinite, then you get overall zero entropy production. If not, you have corrections. So first order correction for long cycles. Then you can again compute power and efficiency at maximum power. And it's interesting that, well, you can expand, you get an expression that you can, and you can study the limit where dissipation is essentially in the, when you are in touch with the cold reservoir, and we are in touch, and when you are in touch with the hot reservoir. And of course, the second upper bound is more favorable, because if you dissipate to the hot reservoir, somehow you can reuse the heat you have dissipated. And here are the regions in between these two limiting values. And again, when you go to linear response, you get eta C over 2, which seems universal. For symmetric dissipation, you get Curzon-Albon. And, well, it's funny that if you look, these are experimental points. They correspond to various thermal power plants all over the world. And they are quite inside this region, which is, if you think about, is quite natural because you try to make this plant to work at maximum output power. This is quite a reasonable request. So there's no universality anyway beyond linear response. So now I try to make similar arguments, but now for steady state power production. So I will frame discussion in thermo-electricity, but you can think about thermodiffusion or other processes, thermo something, to couple flows. So efficiency is power divided heat extracted from the hot reservoir. And okay, I assume that the left is the hot reservoir. And if I will focus on power production, and so power and extracted heat from hot reservoir are positive. Again, the upper bound to efficiency is given by Carnot, as in the previous case, of course. So the question is, what is ideally the best you can do if you look at properties of your working fluid? I mean, I'm not discussing phonons. I will focus on the properties of the working fluid. And an answer was given in this paper more than 20 years ago by Macan and Sofo, and they wrote that delta-shaped transport distribution maximize thermoelectric properties. So the idea is that in this case, you have maximum thermoelectric efficiency. So the question is, this was related to efficiency. So the question is it again the case if you look at trade-off between power and efficiency? So we already had tutorials about energy filtering yesterday, but just to repeat and set notation if you want. You can derive easily this energy filtering within Landauer formalism. So you have you can write a charge and heat currents in terms of transmission probability from a particle with energy E to go from left to right reservoir. And transmission is upper bounded by the number of transverse modes. And then you have difference between Fermi distribution of the particles injected from left and right reservoir. So you can write this expression, and then out of that you can compute efficiency. Power, so is voltage time electric current divided heat extracted from hot reservoir. You have this expression. And then what is delta energy filtering? If you assume that transmission is possible only inside very tiny energy window around some E star value, then you can simplify, of course, this integration, and you get this expression for efficiency. If on top of that you impose the limit of zero particle current, which corresponds to reversible transport, then you fix this the value of energy where you have the filtering, and you insert this value of energy and you get Carnot efficiency. So this is fine because Carnot efficiency is obtained in a limit of reversible transport. So no entropy production and zero output power. So say it's consistent at least. Now if you want to think about energy filtering is needed for thermoelectricity, you can look at this cartoon by Rob Whitney. And if you have a contact between hot and cold reservoir, if you do not put any energy filtering, then you have particle-hole symmetry. So you have flow of electrons from hot to cold and flow below the Fermi sea from cold to hot. So overall you have heat flow but no flow of charge. If you want also flow of charge, you have to put some energy filter, and so depending how you put the the voltage between hot and cold, it can work either as a heat engine or as a refrigerator. But anyway, you need some energy filter. Now, again about the question of power efficiency trade-off. So the first remark is that there is, if you look at quantum, there is a purely quantum upper bound on the heat current that can flow through a single transverse mode. This is known as Bekenstein-Pendry bound. And basically it comes from heat conductor, heat quantization. And the idea is that if you have a reservoir coupled to another reservoir at 0 temperature through n-mode constriction, less particle flow at all energies without any filtering, you have this maximum heat. Then, of course, if heat is upper bounded, then the efficiency is upper bounded too by Carnot efficiency, and so also the power must be upper bounded. Then you can work out this within scattering theories, was done by Rob Whitney a few years ago in these two papers, and then you can set the value of maximum power, which is proportional to the number of transverse modes and to the temperature difference between hot and cold reservoir. Now you can raise the following question. You give the power, of course, smaller or equal than this maximum output power, and you want for that given power to optimize the efficiency. So you want to find the optimum power efficiency trade-off. So you assume that there is a completely arbitrary transmission function, so you have to optimize a functional. And it turns out, if you perform following these papers, the optimization, that the optimum transmission function is a boxcar form between the energy which corresponds to reversible transport and some other energy. So when you shrink the width of this boxcar to a delta, you get 0 power and Carnot. When it is a step function transmission between this energy and infinite, then you get maximum output power. And of course, you deteriorate efficiency. So from the second law of thermodynamics, we know that for a given power, efficiency must be smaller than Carnot efficiency. If you assume scattering theory, then you get a more restrictive upper bound, which is if you expand around 0 power is a square root, so it's quite restrictive upper bound. And these loops are, you increase the voltage, so if you have 0 voltage, you do not produce power. If you increase the voltage, you increase the power production. And then if you increase too much the voltage, you arrive to a stopping voltage where heat temperature difference is no longer sufficient to drive particle current against this voltage. And so you get these loops. If they are optimal along with this boxcar transmission function, then you touch the bound. If not, you get something worse, of course. This is maximum power, so it's a step transmission function, this one. And here is you approach Carnot, so approach delta energy filtering and power goes to 0. Of course, if you add phonons, this is with no phonons. If you have phonons, of course, when you shrink to a delta transmission function, current goes to 0, so sooner or later phonons will dominate. Of course, if phonons dominate, are strong, then it's good to work with maximum power output. But anyway, thermoelectric conversion will be very bad in this, under this condition. Then you can say how you can realize in practice this energy filtering. You can think about several possibilities. I took this one from the literature. If you want, is quite interesting. They assume that it was purely theoretical, of course, proposal. You have a graphene nanoribbon with heavy atoms to have topological insulator. And then you have nanopores. So the idea is that with nanopores, you cut heat transport due to phonons. And and current is transport is dominated by edge states. And so you get a boxcar. And from this numerical simulation, they got ZT of the order of 3 at temperatures of 40 Kelvin. So it was just, of course, was just theoretical proposal, but just to have an idea. So the question I want to discuss in what follows, these are rather recent results, but they raise a question. Is it possible to overcome this non-interacting bound? Because the bad point about this bound is that if you go to power much smaller than maximum power, so you approach Carnot, you approach Carnot with this square root of the ratio of temperatures correction. So it's severe limitation. But the question is that why do you have this bound? The point is that to approach Carnot, you need energy filtering. And since you have energy filtering, you shrink your transmission function. This means that you reduce very much the power. So this is related to the question, can we have Carnot without energy filtering? For non-interacting systems, we know from work of Machen and Sofo, which you cannot. But of course, the question remains for interacting systems. And that's what we discuss. I need, simulation I will show are not limited to linear response. But I need some linear response to make some theoretical argument. So within linear response, we have this couple, energy and heat flows. They are linearly connected to thermodynamic forces, which are basically voltage and temperature difference. They obey Onsager relation. I will consider only system with time reversal symmetry. And you have constraints from positivity of entropy production, of course. Out of that, you can build more familiar transport coefficients, so isothermal electric conductance, thermal conductance, and zero. This is computed at zero particle flow. This means that it has this quite peculiar shape where the determinant features. This is the determinant of these kinetic coefficients. Okay, Onsager coefficient. Somehow this is called the Onsager matrix. And then, of course, you have the thermopower, which is the ratio between of diagonal and diagonal matrix elements. Then the question is if you can work with conductivities rather than conductances. And if you can substitute temperature difference and electrochemical potential difference with gradient. And the question, of course, is if you have, and then speak about conductivity, electric and thermal conductivity. And the question, of course, is related if you have local thermal equilibrium. But this question I want to mention here because it's related somehow to compare traditional with quantum thermoelectricity. Say if you consider traditional thermoelectricity, you have a relaxation length, which are maybe tens of nanometers at room temperatures. They are of the order of a mean free path. Electrons are thermalized due to scattering with phonons. And this relaxation length is much smaller than the size of your system. On the other hand, if you go at low temperature, you consider some quantum thermoelectrics. You can have a relaxation length, which can be larger than the size of your system, and so you have, in principle, to take into account interference effects and so on. So this is also related if you can apply a linear response. Because this is an example, this was a project, I took from this paper a few years ago. It's a project from BMW to reduce fuel consumption using thermoelectrics. And hot temperature is exhaust gases is maybe 700 Kelvin. Cold temperature is room temperature, so maybe 300 Kelvin. If you take this temperature difference and you compare with the average temperature, then it's not negligible, of course. So you should say that you cannot apply linear response. On the other hand, if you compare the temperature drop on the scale of the relaxation length, you can have different conclusion, because assume that the temperature drop is over a millimeter scale in your exhaust. And the temperature drop and the relaxation time scale is maybe 10 nanometers. So the temperature drop over the relaxation time scale is 3 times to the minus 3 Kelvin. So it's completely negligible with respect to average temperature. So this question also if you can apply a linear response, and I will be back later. So within linear response, you can again consider question of maximum efficiency and efficiency and maximum power. Within linear response, it's easier to get, you can get some universal results, I mean. Here I write power is voltage times electric current divided heat current, and I substitute for electric and heat current expression from linear response. Then I say, okay, temperature difference is given, but I can optimize efficiency. I want to find maximum efficiency. I can optimize over the voltage I apply for a given temperature difference. And then you get the maximum for some ratio between voltage and temperature difference, between thermodynamic forces. You can substitute and you get this expression for maximum efficiency, which is a monotonous growing function of this parameter Zt, which is a ratio between electrical and thermal conductance times thermopower squares times temperature. Or if you think in terms of Onsager matrix element, is of diagonal matrix element square divided determinant of the matrix. If you think about restriction from second law, positivity of entropy production just implies that Zt must be greater than 0. And if Zt goes to infinite, eventually you recover Carnot. Of course, if you compare with the bulk thermoelectrics, semiconductors, P and doped, you have on a broad range of temperatures, but you can have Zt of the order of 1, which means, of course, efficiency may be 1/6 of Carnot efficiency. So, of course, to improve efficiency is an issue. But then you can think about previous question, which was look at the efficiency at the maximum power. So you consider again output power within linear response, and you want to find the maximum of power over the voltage you apply for a given temperature difference. And you achieve a maximum, which is given by this expression, so it's determined, but it's proportional to temperature difference square, and is determined by this power factor, which is the product of thermopower square times electric conductance. And basically what you have is that if you look at power within linear response as a function of voltage, you have this parabolic shape. And this is the voltage is a stopping force, which means that you have temperature difference, you increase your voltage, and at some point temperature difference is not sufficient to drive flow of charges against the voltage. This is the stopping force. And at half of the stopping force, you have the maximum power. And then you can compute the efficiency of maximum power, and again, is a monotonous growing function of Zt. First consideration is that Zt is really figure of merit for thermoelectricity, if you remain within linear response. Second consideration is that when Zt goes to infinite, you get again this Carnot efficiency divided 2 that we obtain also for cyclic engines. So it's really some universal result. Of course, if you are at small Zt, if you look at maximum efficiency or maximum power, doesn't make much difference. But if you increase Zt, of course, it's different, because, of course, one saturates to Carnot and the other at half of Carnot. Okay, now there is this, I want to comment on these loops. Okay, you can look at the ratio between voltage and stopping voltage, and you can express power over maximum power as a function of this ratio. You can invert, you plug in into linear response relation, and you can draw universal curves, efficiency in terms of Carnot efficiency divided as a function of power divided by maximum power. And these curves only depend on the parameter Zt. So if Zt is small, say Zt is equal 1, you have these curves. Efficiency is never large, no? Because maybe it goes maybe to 18%. If you increase Zt, you have higher and higher efficiency. And in the limit Zt that goes to infinite, you have a single branch curve. Here you have, at maximum power, you have half of Carnot efficiency, and then you get Carnot efficiency and 0 power. So the point is that here, as a function of power, if you look at low powers, you start from Carnot, your efficiency drops linearly with the power, which is much better than the bound from scattering theory. So the question is if you can approach somehow this result, which is ideal within linear response. And so the idea is to look at interacting systems. Okay, I need
sorry, I do not understand, but can you have cases in which it's not linear, but it's nearly quadratic or something?
This I cannot exclude, of course. No, this is a universal within linear response. Then I cannot exclude that you can have some, you can find some...
No, I'm asking if there are cases in which linear response is never there. So you start quadratic, or cubic, whatever.
You mean here?
Yeah.
No, here you have this, this bound from scattering theory. Where was it? You start as a square root. This is non-linear scattering theory. The point is that when you approach Carnot, the validity range of linear response shrinks. No? So you have this. So you start less than linear. Is less favorable than linear.
Right. So can you have the other way around?
This is a question. I don't know. I cannot exclude. No, it's not forbidden from thermodynamics. Then if there are other reasons to forbid it, this I don't know. But I cannot see a reason from thermodynamics that forbids this possibility. And so if I come back, okay, now I need another ingredient, but this is just to get some analytical prediction. It's just use a Green-Kubo formula to compute linear response transport coefficients. And so the point is that you can have generalized through the weight, so delta peaks and 0 frequency. And when you have this is a signature of ballistic transport. Then I need another ingredient which you can compute through the weight for finite size systems. As a function, you can use this expression, which is in terms of constant of motion, which are non-orthogonal to the currents you are considering. Here you have particle and heat current. Non-orthogonal means that when you take a thermodynamic expectation value at a given temperature, you get a non-zero result. And then, of course, there is another non-trivial point, is that in principle, to compute the through the weight, one should before let the system size to infinite and then the time to infinite. And here I will assume the commutativity of the two limits to obtain the thermodynamic through the weight as limit of the finite size through the weight. And this, of course, could be an issue. And then the other remark is that if I consider system where this sum is just limited to 1, so typically you can imagine a system where you have only elastic scattering, so momentum conservation. Yeah.
I'm sure you need the other order of limits, because I think you can do the first one.
Well, in principle, if you think about thermodynamic,
I think there is nothing against doing the standard
you mean that there's nothing against exchanging the order of this limit?
You are saying that you have to change the limits. You have to first take the thermodynamic limit.
But in principle, you should first take the thermodynamic limit.
I think you can.
Yeah, but I mean, if I don't, I can use this formula, because this formula was derived for finite size systems. Okay, because they look at a spectrum of the finite size system. If I exchange the order of the limits, I cannot build a. Yeah, I cannot build a theory. Yeah, that's the point. No, I can only say that in all the cases I.
In general, they do not commute.
Yeah, no. What I can only say is that in all the cases we checked, we found this. But of course, you can have counterexamples.
Okay, also you need complete set because of quantities. You have an equality, you need complete set.
Yeah.
You are never sure how you have complete set.
Yeah, of course. No, of course. That's why we needed some numerics. Otherwise, no. But then the point is that if you have just a single constant of motion, so elastic scattering, you have momentum conservation and a non-integrable system. Then you have a cancellation because in the heat conductance or conductivity you have a determinant which appears. And so you have conservation of the contribution due to the weight. So you can say predict that for heat conductivity it goes less than ballistically, the growth with the system size lambda. While for charge conductivity it goes ballistically, and thermal power, which is the ratio to transport coefficiency, should become asymptotically size independent. So the prediction is that ZT with the system size diverges because the ratio of conductivities diverges. You go towards a regime where you strongly violate Wiedemann-Franz law, you can also say like that. Okay, for integral it doesn't work. So to check just the first example, we consider a one-dimensional gas of unequal masses elastically colliding, coupled to reservoirs. So if masses are equal, you have integrable model. You can compute trivially heat or energy and particle flow, and you get ZT equal 1 at mu equals 0. So it's trivial result, nothing interesting. But if the system is non-integrable when you have unequal masses, so ZT depends on the system size. Here simulations are not limited to linear response. So when particles hit the boundaries, they are absorbed and they are injected with some injection rate. Calculations are purely classical. So you have ideal gases for your reservoir, so Maxwell-Boltzmann distribution of velocities. You can determine injection rate. But what I want to say is that some quantum element is needed because otherwise some arbitrary constant remains in the electrochemical potential. So if you start from the grand partition function, you have to put this 1 over n factorial, and this is related to indistinguishability of particles, so it has nothing to do with classical mechanics. It's some quantum ingredient you put. And if you put this ingredient, you can relate electrochemical potential to particle density via the de Broglie thermal wavelength. And then you can, for instance, compute correlation function, particle-particle, energy-energy, particle energy as a function of time, and they do not decay. And okay, these are different system sizes, and they are on top of each other. So this is some indication that for this model you can exchange the two limits. Then you can compute transport coefficients. So electrical conductivity is ballistic, thermal power saturates, thermal conductivity grows with 1/3 exponent expected from hydrodynamic theories. Then you make this ratio, and then the ZT increases like system size to the power 2/3. So the point is that this has apparently nothing to do with energy filtering, because if you look, for instance, temperature along your sample, these are different system sizes. You get some distribution. You have some local thermal equilibrium, say. Okay, you have some contact resistance, of course. And then you can look at distribution of velocities for your for the two masses at some point along your sample. This is for the two system sizes, and you fit very nicely with Maxwell-Boltzmann distribution. So apparently there's no energy filtering here. So if there is no energy filtering, you have hope that the power efficiency trade-off is better. Well, so this is just some plot, temperature difference voltage for efficiency and power. And you see that you can have regions where it is good for power and other where it is better for efficiency. So you have to find some trade-off. And then, okay, first of all, we check validity of linear response. So here are curves from linear response at the value of ZT that you determine numerically, and then you compare with what you measure for efficiency and power. And you see that if you go with larger and larger system size, you increase the ZT, but also you approach your linear response works better and better, which is in a sense reasonable because gradients, temperature gradients decreases as the system size increases because you keep constant temperature difference. Then you can derive bounds. You can work out bounds as was done in the quantum. So you have some formula which is analogous of the Landauer formula for classical. So you have injection rate and energy distribution of injected particles. And out of that, you can compute charge and heat current. Of course, you will have Maxwell-Boltzmann distribution rather than Fermi-Dirac. And then you have this kind of bound. Again, is a square root. It goes like 1 minus square root of temperature ratio. So again, the bound from scattering theory is quite unfavorable. And then you can compare. Okay, this is result is the bound from scattering theory, so for non-interacting. This is expansion as small power, and this is what you get for interacting. And this is expansion for a small power. So basically, for each system size, what we did, we look just to show that also for finite system size, you are beyond this bound. You can, for instance, look at points where the efficiency is maximum. So in this course, you take, I don't know, this point, this point, this point where efficiency is maximum. Then you compute the power at maximum efficiency, and you get this point. And this is some, you can work out easily analytically from linear response, and you approach the asymptotic behavior, which is linear from linear response. So you can overcome this bound. These are just, we just put some probability to interact or not interact. So basically you scale, you need larger system sizes, sometimes particle can not interact. And then of course one could say this is, because the model is one-dimensional, is very spatial, you can say there is some dimensional issue, but actually this is not the case, because we check, for instance, this other model. This is two-dimensional, is Capral model. And is some clever model to simulate interacting particles in 2 or 3 dimensions. And you divide, basically you discretize time and the time of interactions. And then you, so you have streaming steps where you have free propagation. Then you divide your system into cells. And then you look at, after a free propagation, you have collision step. So you look at particles inside the cell, and you randomly rotate the velocities of the particles in cells, in each cell, with respect to their center of mass velocity. So this plus or minus rotation angle, this gives you interaction strength, basically. And of course, this is a momentum conserving system, so previous theory should apply. And so you can repeat all this analysis. You can, for instance, verify that you obtain data which are in very good agreement with linear response. Then you can rederive the scattering theory bound in 2 dimensions. Well, it's a little bit more involved, but you can consider free gases and injection, a fusion process injection through these openings. And then you can derive this bound. And then you get this point, efficiency versus power, and you go beyond this bound, and this is again the asymptotic behavior. These are 2 kinds of points. In one case, we computed directly looking at this picture where you have maximum efficiency. In the other case, we extracted from linear response, so just to check that you get a compatible result. So it seems that this result is rather generic, so that thanks to interaction, it is possible for a given power to overcome the bound on efficiency which applies for classical non-interacting systems. This is first conclusion. Then this, and we approach this power efficiency trade-off, which is optimal within linear response. Of course, we cannot exclude that beyond linear response one could do something better. Okay, I didn't show here, but we can. We are working now, but you can extend also these results to cooling. So in that case, the question is you set the cooling power, and you ask what is the maximum efficiency you can get for a given cooling power. And again, you can overcome the bound due to scattering theory. And at the end of the game, the physical reason why you get this improvement is because in this interacting system you can get Carnot efficiency without delta energy filtering. This is the key difference. Of course, it remains open the question if you can extend these results to purely quantum systems. This, of course, is an open question. Okay, if you have questions. Thank you.